Hello and welcome to the Autodidact Scientist Algorithm series, where I will be giving you an intuitive insight into a variety of algorithms that are used for machine learning. I'm your host, Rich Gregson. And before we get started, as always, I would greatly appreciate if you would like this video and subscribe to the channel. So what are we going to cover today? The algorithm we're going to be taking a look at today, a support vector regression. Now, in classification issues, support vector machines are well known, but SVMs for regression analysis, not very well known. And even now, when I mention support vector regression in front of newcomers to machine learning, more often than not, I see puzzled faces. Now, I realize that support vector regression isn't even mentioned on most courses or even by professionals as a machine learning algorithm, but SVR does have its uses, as you'll see in this video. So what is support vector regression? I'll start by providing a basic summary of SVM. So suppose we've got a plot of with two labeled classes, like in the figure here. Now, where would you put a classification line to classify these two groups of data? Now, you'd probably put it somewhere like that. The division of classes along this line, it's fair. It's a simple class separation, and that's essentially what SVM accomplishes. Now, take a look at this image here. What if your data looked like that? Now, there isn't just a straight line dividing these two classes. And so in order to do this, what we need to do is expand our dimension and add a new dimension line across the along the z-axis, which you can see here. So now these two classes can be distinguished. So when we transform the line back to its original plane, it maps to the circular boundary, which you can see here. And that is what SVM does. In a multi-dimensional space, it looks for a line or hyperplane that can divide these two classes, and then it uses those classes to forecast. So it basically assigns the new point a classification based on whether it's located on the positive or negative side of the hyperplane. So what are the hyperparameters of support vector regression? The first one is a kernel. And what a kernel does is basically help us find a hyperplane in a higher dimensional space without increasing computational cost. Usually the computational cost will increase if the dimension of the data increases. And this increase in dimension is required when we're unable to find a separating hyperplane in a given dimension. Therefore, we have to move into a higher dimensional plane. So the most popular kernels to use are linear, nonlinear, polynomial, radial basis function, and sigmoid. The radial basis function, also known as RBF, is the default parameter of the kernel. The next one is the hyperplane. In SVM, a hyperplane essentially acts as a boundary between two data classes. However, in SVR, the hyperplane is utilized to forecast the continuous output. The third one is the decision boundary. To simplify, think of a decision boundary as a line where the positive examples are on one side and the negative examples are on the other. The instances can be categorized as either positive or negative along the decision boundary, and we can tune the decision boundary to gain the desired accuracy of our model. So let's talk about using support vector machines for regression problems. Now, finding a function that roughly maps an input domain to actual numbers using a training sample is the ultimate goal for regression analysis. So let's examine the SVR in a little bit more detail and learn how it actually functions. So as you can see on screen, we've got a plot and a couple of equations. So the red line in this plot is the hyperplane, and the two grey lines are our decision boundaries. So when we use SVR, our goal is to essentially take into account the points that are inside the decision boundary lines. The hyperplane that has the most points serves as our best fit model. So think of the decision boundary lines as being at any distance from the hyperplane. And that is known, the distance between the decision boundaries and the hyperplane are known as the ellipson. The lines that we draw at the positive ellipson, which is this one here, and the negative ellipson, which is this one, can be calculated using the equations on screen. So assume that the equation of the hyperplane is our first bullet point. Now the equations of the decision boundaries, both positive and negative, become our second and third bullet points. And therefore any hyperplane that satisfies our SVR should be taking the form of our fourth bullet point. So again, we only consider points that are in our decision border. We also consider ones that have the lowest error rate or fall within the margin of tolerance. And if we do that, we have a model that fits our data very well. Now, the data points, as you can see here, just as I've circled, these fall outside our decision border, and these are known as slack variables. And the concept of slack variables is simple. For any value that falls out of the ellipson, we can denote its deviation from the margin using the symbol here, which is called xi. So we know that these deviations have, they do have the potential to exist within our data, but we would still like to minimize them as much as possible. So we can add these deviations to our objective function, which gives an additional hyperparameter, usually known as C, and we can tune that. So as we increase C, the tolerance of the points outside our decision boundaries increases, and therefore we can capture them particular outliers within our model. So what are some of the advantages and disadvantages of using SVR? So as we've seen, SVR is robust to the outliers. The decision model can be easily updated the way I've just demonstrated. And it can use multiple classifiers trained on different types of data using the probability rules. It can improve the prediction accuracy by measuring the confidence within the classification. SVR, support vector regression, can perform in a lower computational environment compared to other forms of regression. And of course, its implementation is very easy. For the amount of power SVR SVM holds, its implementation is probably one of the most easiest we can do, either using scikit-learn or completely from scratch using the mathematical functions in NumPy. So of course there's no free lunch. What are the disadvantages? So they're not suitable for large data sets, and it will underperform when a number of the features for a data point exceeds the number of data samples, and it doesn't perform very well when the data set has a lot of noise, for example when the target features overlap. So that concludes the video on support vector regression, where we've understood that SVR is one of the most useful and flexible techniques for regression problems. I think one of the most important things to take away from this before you implement SVR is that the choice of kernel plays a crucial role in SVR modeling. Now, I'm also going to do a video on SVM, support vector machines, for classification problems. So please keep an eye out on that for that one. And I appreciate, of course, everyone who's taken the time to watch this video. And I would appreciate it if you liked, shared, and subscribed to this channel. And if you have, of course, if you have any questions, comments, or feedback, please hit me up personally on Twitter or contact me through any of the Autodidact Sciences channels. Thanks very much for watching.